Good morning, class. Welcome to the chapter 3 of our probability and statistics class. So, for this chapter, we're going to discuss sampling and sampling distribution. In our earlier study of statistics, we have learned about frequency distribution. In chapter 1, we also learned about probability distribution. And in this chapter, we're going to discuss another kind of distribution, which is sampling distribution of the means. We will learn how to describe the sampling distribution of the means by computing its mean and standard deviation. So for our first lesson, our topic will be sampling distribution of sample means, and our objectives are illustrate random sampling, distinguish between parameter and statistics, and construct sampling distribution of sample mean. So researchers use sampling if taking a census of the entire population is impractical. Data from the sample are used to calculate statistics, which are estimates of the corresponding population parameters. For instance, a sample might be drawn from the population. Its mean is calculated, and this value is used as statistics or an estimate of the population mean. Thus, descriptive measures computed from a population are called parameters, while descriptive measures computed from a sample are called statistics. So we can say that the sample mean is an estimate of the population mean mu. So the number of sample size n that can be drawn from a population of size n is given by a combination formula. So n choose n. And sampling distribution of sample mean is a frequency distribution using the means computed from a possible random samples of a specific size taken from a population. Probability distribution of sample means is also called the sampling distribution of the sample mean. Lastly, sampling error is the difference between the sample mean and population mean. Its error is due to sampling. So here are the steps in constructing the sampling distribution of the mean. First is to determine the number of possible samples that can be drawn from the population using the formula, a combination formula. So n choose n, where n, the big N, is the size of the population and is the size of the sample. Second, list all the possible samples and compute the mean of each sample. Third, construct a frequency distribution of the sample means obtained in step 2. So let's have two examples so we can understand what I am talking about. Example number 1. A population consists of the numbers 2, 4, 9, 10, and 5. List all the possible samples of size 3 from this population and compute the mean of each sample. So if you remember our first chapter, we discussed about random variables and how to find the possible outcome. So for this question, we're going to do that as well. Okay, so we have a possible outcome of 2, 4, and 9. We have 2, 4, 10, 2, 4, and 5. We also have 2, 9, 10, 2, 9, 5, and 2, 10, 5. Okay, let's go to number 4. We have 4, 2, 9. So we already have 2, 4, 9. So it's just the same. We will have 4, 9, 10. We will also have 4, 9, 5. And then let's go to 9. We have 9 to 4. Let's see if we'll already have. So we have here. So it's just the same. 9, 4, 10. We also have that. So 9, 10, 5. And lastly, we forgot to include the 4, 10, 5. Okay, so we already identified that there are 10 possible outcomes of size 3 that can be drawn from the given population. Now, let's find the mean. And how do we find the mean? So, that is the summation of your sample divided by the total number. So, for this, we add 2 plus 4 plus 9. 2 plus 4, it's 6 plus 9, that's 15. Divide by 3, so that will be 5.00. So let's add two decimal places. So we're going to do that for the rest. So 2 plus 4 plus 10. So for this one, the mean would be 5.433. So you can try it on yourself to verify if the mean is correct. Okay. Next, we have 3.67, 7. Next, 5.33. And then for the mean of 210.5, that is 5.67. For the 2910, that is 7.67. That this one is 6. This one it's 8. And lastly, it's 6.33. So, as I discussed earlier, the number of sample size n that can be drawn from a population of size n is given by n choose n. So, this time, let's make a frequency distribution of the sample means. We shall call this frequency distribution the sampling distribution of the sample mean. We have the mean or the sample mean already. Let's arrange it into ascending order, meaning from the lowest up until the highest. So we're going to find the frequency distribution of the means, or if we remember, that is the sampling distribution of the means. Frequency distribution tells us the frequency of various outcomes in a sample or the number of times they occur. So for this one, 3.67 occurs only once. Where that is? So in 2, 4, 5. So in this sample mean, okay? Next, 5 occurs only once. For 5.33, it occurs twice for the sample mean of 2,410 and 295. And for the rest, it only occurs one. If you're going to add this up, the total of days would be 10. So the sampling distribution of sample mean is a frequency distribution using the means, computed from all possible random samples of a specific size taken from a population. So if we're going to observe that the means vary from sample to sample, thus any mean based on the sample drawn from a population is expected to assume different values for the sample. So this leads us to a conclusion that sample mean is a random variable. Remember, your samples came from the possible outcomes, and we discuss it to our first chapter, which is random variable. Okay, which depend on a particular sample. Being a random variable, it has the probability distribution, which we discussed on our on our first chapter as well. So the probability distribution of the sample mean is also called the sampling distribution of the sample means. Okay, let's construct a sampling distribution of a sample mean table with its probability distribution. And how do we compute for the probability of your sample mean? That is the number if occurs over the total number of the possible outcomes. So for the 249, it occurs only once. So that will be 1 over 10, or that is 0.10. So for this one, 1 over 10, 2 over 10, that is 0.2 or 0.20. So same. 1 over 10, 1 over 10, 0.10. Okay, and for the rest. Okay, so it will give us a total of 1.00. So observe that the means of the sample are less than or greater than the mean of the population. The difference between the sample mean and the sample population is called the sampling error. So it is the error due to sampling. Let's proceed to example number 2. Samples of 3 cards are drawn at a random from a population of 8 cards numbered from 1 to 8. So this question will give us a lot of possible outcomes. So we're going to use the combination formula, that is n choose n, where your n, the big N, is the size of the population and the small n is the size of the sample. So let's identify the given. You're given, based on the statement, the size of your population will be 8 and the size of the sample would be 3. So if you're going to compute that, the combination formula in your calculator, it will give you an answer of 8 choose 3 of 56. Now let's try to compute it manually, just to review you on your past lessons about probability. Okay, so this formula, n factorial over n factorial, big N minus your n factorial. Okay, so let's try to compute it. That is 8 factorial over 3 factorial, 8 minus 3 factorial. So here, let's have 1 times 2 times 3 times 4 times 5 times 6 times 7 and then times 8. So this is basically the factorial. And then 1 times 2 times 3. Multiply by, so 8 minus 3, that is 5. 1 times 2 times 3 times 4 times 5. Or simply, we can write this as 8 factorial over 3 factorial times 5 factorial. So it will give us an answer of 40,320 over 6 times 120. So 6 times 120, that is 720. And the result for this is 56. So that's how you compute manually the combination formula. But for you to make it easier, do it on your calculator. Okay? We already know how many possible samples that can be drawn, which is 56. For our second step, we're going to construct the sampling distribution of the sample mean. So if you remember on our first example, we list down all the possible outcomes and then compute its sample mean, and then identify the frequency and the probability distribution. So I already did the table for this, because if we're going to do that, that would be a lot. Okay, so you can try it on your own to check if the list of sample mean, the frequency distribution, and the probability are correct. So for our last, we're going to construct the histogram of the sample distribution of the means. So how do we construct the histogram? Excel in doing that. This will be the frequency distribution or the histogram of the sampling distribution of the mean. So for your x-axis, that will be your sample mean, and for your y-axis, that is the probability distribution. So if you can observe, there are highest number of the mean are located here between 4 and then 5. Statisticians don't just describe the variation of the individual data values about the mean of the population. They are also interested to know how the means of the samples of the same size taken from the same population vary about the population mean. So in this lesson, our second lesson, which is finding the mean and variance of the sampling distributions of mean, we will learn how to describe sampling distribution of the sample means by computing its mean and variance. We will also make a general conclusion regarding the mean, variance, and shape of the sampling distribution of the sample mean. So we have two objectives, that is find the mean and variance of the sampling distribution of the sample means, and state and explain the central limit theorem. So let's have examples for these lessons. For example number one, let's consider a population consisting of 1, 2, 3, 4, and 5. Suppose samples of size 2 are drawn from this population. Describe the sampling distribution of the sample means. So first, we're going to find what is the mean and variance of the sampling distribution of the sample means. Second, compare these values to the mean and variance of the population. Lastly, draw the histogram of the sampling distribution of the population mean. So first, we're going to compute for the mean and variance of a population. So how do we compute it? So let's have letter A. So mean of the population. And the formula for that is mu equals to the summation of your population over the total number of outcomes. So that is, we have 1, 2, 3, 4, 5 over 5. Okay, so 1 plus 2, that's 3, plus 3, that's 6, plus 4, that is 10, plus 5, that is 15. Divide by 5, so it will give us an answer of 3. So therefore, the mean of your population is 3. Next, we're going to compute for the variance of the population. So variance of the population. So what is the formula for the variance of population? That is, we're going to make a table for this one. Okay, so we have our random variables x, we have 5. Okay, so we have 1, 2, 3, 4, and lastly 5. And we're going to subtract the random variable to our mean. So 1 minus 3, that is negative 2. 2 minus 3, that's negative 1. 3 minus 3, that's 0. 3 minus 3, 4 minus 3, that is 1. 5 minus 3, that is 2. And then we're going to raise the answer for this. So negative 2 raised to 2, that is 4. Negative 1 raised to 2, that is 1. 0 raised to 2, that's 0. 1 raised to 2, that's 1. 2 raised to 2, that is 4. And then we're going to find the summation of this. So, summation of x minus mu, your random variable minus the mean, squared. So 4 plus 1, that is 5. And then 6 plus 4, that is 10. So your answer will be 10. But that's not yet the variance. So the formula for the variance, that is summation of your x, random variable x minus u, raised to 2 over n, or the total number of your outcomes. So that is 10 divided by 5. And it will give us a variance of 2. So therefore, the mean of your population is 3 and the variance of your population is 2. Next, we're going to determine the number of possible samples of size n, which is 2. So we're going to use the formula of the combination, that is n choose n. So your n, or the size of your population, would be 5, and the size of your sample mean will be 2. So 5 choose 2, that is equal to 10. So we can say that there are 10 possible samples of size 2 that can be drawn. So next, we're going to list all the possible samples and their corresponding means. For this, we have samples of 1, 2, we have 1, 3, 1, 4, 1, 5. Okay, let's have another one, 2, 1. So we already have 2, 1, which is 1, 2. The same. Let's have 2, 3. Next, it's 2, 4. Next, it's 2, 5. For 3, we have 3, 1 already, or 1, 3. We have 3, 2, which is 2, 3. Let's have 3, 4, 3, 5, and lastly, 4, 5. Because we already have 4, 1, which is 1, 4. We already have 4, 2, which is 2, 4. And we already have 4, 3, which is 3, 4. And then we're going to compute for its mean. So how do we compute again for the mean? Let's add the summation of your outcomes over the total number of outcomes. Okay, so 1 plus 2, that's 3, divided by 2, that is 1.5. And then you're going to do it for the rest. So let me put it. So 2.00, that is 2.5, that is 3. This one, it's 2.5. Next, we have 3, 2 and 5, that is 3.50. 3 and 4, that is 3.50. 3 and 5, that's 4. And 4 and 5, that is 4.5. So next, we're going to construct the sampling distribution of the sample mean. So how do we do that? We do the frequency table and the probability distribution. We have the following sample mean, which is arranged ascending order. So we have 1.5 or 1.50, 2, 2.50, 3, 3.50, 4, and 4.50. So the frequency for 1.5, it only occurs once. So where this is in 1 and 2. So for 2, it also appeared once. It's 1 and 3. For 2.5, it appears twice. So where in 1 and 4 and 2 and 3. So for 3, it also appeared twice. That is for 1 and 5 and 2 and 4. For 3.50, it appears also twice. That is 2 and 5, 3 and 4. For the sample mean of 4, it appeared once. So in 3, and 5. And lastly, for 4.50, it appeared 1. So that is 4, 4, and 5. And to compute for the probability distribution, that is your frequency over the total outcomes. So we have the frequency of 1, that is 1 over 10. We also have 1 over 10. The next for 2.5, the sample mean of 2.50 or 2.5, that is 1 over 5. So same. For the rest, you're going to compute it. And it would give you a summation of 1.00. Next, we're going to compute the mean of the sampling distribution of the sample means. So we're going to follow the steps. First, we multiply the sample mean by the corresponding probability and then add the results. Sample mean multiplied by your probability distribution. So for this, we're going to multiply 1.50 times 1 over 10, or if you're going to convert this to decimal, that is 0.10, and it will give you an answer of 0.15. So for the rest, you're going to multiply your sample mean to your probability distribution, and then after that, you're going to get the sum of this. Okay, so we can say that the mean of the sampling distribution of the sample mean is 3. Next, we're going to construct the variance of the sampling distribution of the sample means by following this step. So first, we're going to subtract the population mean from each sample mean. So what is our population mean? That is 3. Okay, if you remember. And then what is our sample mean? So here, so we have 1.5, 2, 2.5, 3, 3.5, 4, and 4.5. So we're going to subtract the sample mean to your population mean. So here we have 1.5 minus 3, that is negative 1.50. And then 2.00 minus 3.00, that is negative 1, and so on and so forth. So next steps, we're going to square the difference. So here, so sample mean minus your population mean raised to 2. So okay, so your sample mean, that is, we already have the difference, negative 1.50 raised to 2. That will give you an answer of 2.25. Same that you're going to do for the rest of the sample means. And then for the third step, we're going to multiply the results by the corresponding probability. So probability of your sample mean times the square difference of your sample mean minus your population mean. So we already have this, which is 2.25, and then we're going to multiply it to your probability. So 1 over 10, or 0.10, multiply by 2.25 will give you an answer of 0.225, and so on and so forth. To compute for the variance, we're going to add all of this. And therefore, we can say that the variance of the sampling distribution is 0.75. So we're going to put it into two decimal places. For this question, we compute the mean of the population, which is 3, the variance of the population, which is 2, the mean of the sampling distribution of the sample means, which is 3, and lastly, the variance of the sampling distribution, which is 0.75. Now, we're going to construct the histogram for the sampling distribution of the sample means. For the x-axis, or the horizontal line, we're going to name it or label it as your sample mean. So we have the sample mean of 1.5, 2, 2.5, 3, 3.5, 4, and 4.5. So for the y-axis, or your vertical axis, this will be your probability of the sample mean. Okay, what are those? That is, we're going to have the standard deviation of 5. So we have 0.05, 0.10, 0.15, 0.20, and 0.25. So for the sample mean of 1.5, we have the probability of 0.10. So here, same as sample mean of 2, we also have 0.10. And same, okay, 0.10. However, for the 2.5, we have the probability of 2. Okay? So same with sample mean of 3. We also have 2. And same with the 3.5. So we also have 2. For the 4, sample mean of 4, we have 0.10. Lastly, for 4.50, we have 0.10. So therefore, this is your histogram for the sampling distribution of the sample mean. Let's proceed to example number 2, that is sample means from a finite population. Example number 2. Consider a population consisting of 1, 2, 3, 4, and 5. Suppose samples of size 3 are drawn from this population. Describe the sampling distribution of the sample means. What is the mean and variance of the sampling distribution of the same sample means? Compare these values to the mean and variance of the population. So same question that we have on our first example. The only difference is that the size of the sample mean is 3. For the first example, we have the size of 2. So therefore, the mean of the population would be 3, and then the variance of the population would be 2. So for the possible samples of size 3, we're going to use the 5 choose 3 or our combination formula. So it will give us 10 possible samples of size 3. So next step, we're going to list all possible samples and then their corresponding means. Okay, so we have 1, 2, 3. Next, 1, 2, 4. Next, 1, 2, 5. Um, let's say 1, 3, 4. 1, 3, 5. Okay. Um, 1, 4, 5. So let's try 3, 1, 2. I'm sorry, 2, 1, 3. So we already have it. It's just the same with 1, 2, and 3. Let's have 2, 3, 4. Next, 2, 3, 5. Next, 2, 4, 5. Okay. So let's try 3, 1, 2. Same as 1, 2, 3. 3, 2, 4. Same as 2, 3, 4. 3, 4, 5. So as you can see, we have 10 possible samples of size 3. And then we're going to compute for the mean. Remember, that is the summation of your samples over the total number of possible outcomes. So for this one, 1 plus 2, that is 3 plus 3, that is 6, divided by 3, it will give us an answer of 2.00. So we're going to do that for the rest of the sample mean. Okay, so this one 2.33, 2.67, 2.67, next 3, next 3.33, and then 3 again. For 2, 3, and 5, we have 3.33. For 2, 4, and 5, we have 3.67. And lastly, we have 4. So the next step, we're going to construct the sampling distribution of the sample mean. Let's arrange the sample mean into ascending order. So we have 2.00, 2.33, 2.67, 3.00, 3.33, 3.67, and lastly 4. So for the sample mean of 2.00, it occurs or appeared only once. So where it is? So in the sample of 1, 2, and 3, and its probability is 1 over 10. Next, for the 2.33, it appeared only once as well. So we have 1 over 10. That is your probability. However, for the 2.67 sample mean, it appears twice. So, in 1, 2, and 5, and 1, 3, and 4. So, here. So, therefore, the probability of your sample mean is 1 over 10, 2 over 10, or 1 over 5. And the rest, you're going to do that. So, your total frequency is 10, and then the probability of your sample mean is 1.00. So next, we're going to compute the mean of the sampling distribution of the sample means. So like what we did earlier, so multiply the sample mean by the corresponding probability and add the result. So we already have the sample mean, and then multiply it to probability will give you these answers. And then to find the mean of the sampling distribution of the sample means, we need to add this product. So, therefore, we have the mean of the sampling distribution of the sample mean is 3. Next step is we're going to compute the variance of the sampling distribution of the sample means. We'll be subtracting the population mean, which is 3, from each sample mean. Okay, and then we're going to label it as sample mean minus your mu. Okay, so 2.00 minus 3.00 will give us an answer of -1. Same as 2.33 minus 3.00 will give us an answer of -67, and so on and so forth. So you're going to do that for the rest of the sample mean. Next step is we're going to square the difference, and we're going to label this as squared of your sample mean minus your mu. Okay, so we already have this. We're just going to square this. So -1 squared, that is 1. -0.67, that is 0.44. So any number raised to 2 or any number multiplied by itself, either positive or negative, will result into positive. And then if you're going to compute this using your calculator, you will notice that aside from 0.67, there are still a lot of digits left. So we just round this off into 2 decimal. But remember, when during the process when computing, please don't remove or round this off while doing your operation. So after, or maybe if you that will be your final answers, that's the only time we're going to round this up. But for this one, we just make it simple. Okay, and then the next step is to multiply the results by corresponding probability. So here, we're going to label this as probability of your sample mean multiply by the square difference of your sample mean minus the mu. And then, so 1 over 10 multiply by 1, that is 0.1. 1 over 10 multiply by 0.44, that is 0.04. So for the rest, you're just doing it as well. And then fourth step, you will need to add the results. And having the result or having the sum, which is 0.33, means this is your variance of the sampling distribution of the sample mean. So next step, we're going to construct again a histogram. The sample mean will be placed on your x-axis or the horizontal line, while for the probability of your sample mean, it will be placed on the y-axis, which is the vertical line. Okay, for the sample mean of 2, there will be a probability of 0.10, same as 2.33. Okay, and for the 2.67, 3.33, so we have the probability of 0.20. So here. And for the 3.37 and 4, we have the probability of 0.10. Okay. So, we're going to summarize what we have done for the preceding activities that we have by comparing the means and variance of the population and the sampling distribution of the means. We can observe that the mean of the sampling distribution of the sample mean is always equal to the mean of the population. The variance of the sampling distribution is obtained by using the formula um, square sigma of your sample mean is equal to the square of your variance over the size of your sample multiply. Okay, so let's put it like here, multiply by the size of your population minus the size of your mean sample, I mean, over size of your population minus 1. So this formula holds when the population is finite. The example shown in the preceding activity, so in activity 1 and 2, are all finite population. A finite population is the one that consists of a finite or fixed number of elements, measurements, or observation, while infinite population contains hypothetically at least infinitely elements. So the expression square root of your n or your size of the population minus the size of your sample over size of the population minus 1 is called the finite population correction factor. So in general, when the population is large and the sample size is small, the correction factor is not used since it will be very close to 1. Okay, so here are the properties. So to summarize the sampling distribution, the following are the properties of it. So, if all possible sample size of n are drawn from a population of a size n with the mean and the variance, then the sampling distribution of the sample mean has the following properties. So first, the mean of the sampling distribution of the sample mean is equal to the population mean. That is mu sub your sample mean is equal to your mean or the mu. Okay, so the variance of the sampling distribution of the sample means sigma is given by, so for finite population, so this will be your formula. And for the infinite population, this will be the formula. The standard deviation of the sampling distribution of the sample mean is given by, so here, okay, for finite and infinite population. So, The standard deviation of the sampling distribution of the mean is also known as the standard error of the mean. It measures the degree of accuracy of the sample mean as an estimate of the population mean. Okay? A good estimate of the mean is obtained if the standard error of the mean is small or close to zero, while a poor estimate if the standard error of the mean is large. We can observe that the value of your sigma sub sample depends on the size of the of your sample. What happens to it when n is increased? If we want to get a good estimate of the population mean, we have to make n sufficiently large. This in fact stated as a theorem, so which is known as the central limit theorem. So it says if a random samples of size n are drawn from a population, then as n becomes larger, the sampling distribution of the mean approaches the normal distribution. Remember, we discussed normal distribution on our chapter 2, regardless of the shape of the population. Okay, so we will be having two examples to describe the sampling distribution of the sample means from an infinite population. Example number 1. A population has a mean of 60 and a standard deviation of 5. A random sample of 16 measurements is drawn from this population. Describe the sampling distribution of the sample mean by computing its mean and standard deviation. So first, let's identify the given. So we have the mean of 60, standard deviation of 5, and the size of your sample is 16. Okay, and then next step is we're going to find the mean of the sampling distribution, and to find that we will going to use this property, that is the mean of your sampling or your sample mean equals to your mean, which is 60. Okay, or we can say, we can put it like here. So, mean of the sampling distribution is equal to 60. Okay? Next step is to we're going to find the standard deviation of the sampling distribution. Okay, by using the property sigma, or the standard deviation of your sample mean, is equal to the standard deviation over the square root of your sample. Okay, so standard deviation of the sampling distribution is, okay, let's substitute. So we have the standard deviation of 5 and then square root of r of the size of our sample, which is 16. So square root of 16 is 4. So 5 divided by 4 is equal to 1.25. So therefore, we have this standard deviation of your sample mean is 1.25. Let's proceed to question number 2. Example number 2. The heights of male college students are normally distributed with mean of 68 inches and standard deviation of 3 inches. If 80 samples consist of 25 students, each are drawn from the population, what would be the expected mean and standard deviation of the resulting sampling distribution of the mean? So we're going to assume that the population is infinite. Okay, so let's identify what are the givens. We have the mean of 68 and standard deviation 68 and standard deviation of 3. And then it says that if maybe you're getting confused with this. So if 80 samples consist of 25 students, so meaning your population would be 80, but the size of your sample would be 25. Okay. And then second, we're going to find the mean of the sampling distribution. And again, what's its property? That is the mean of your the mean of your sample mean is equal to your mean, which is 68. Okay. And next, we're going to find the standard deviation of the sampling distribution using this property. So, like what we did earlier on our first example, okay? So, square root of your, okay, what's your standard deviation? That is 3, square root of 25. And the square root of 25 is 5. So, 3 divided by 5 is equal to 0.6. So, therefore, the mean of the sampling distribution is 68. While the standard deviation of your sampling distribution is 0.6. So this is the standard deviation. Okay, let's proceed to the last lesson for this chapter.